This Week in Radio Tech, episode 142, is brought to you by Omnia Audio and the Omnia 9 FM plus HD audio processor. The Omnia 9 delivers more features than ever in a single unit, and it sounds absolutely amazing. Meet the Omnia 9's inventor, Leif Clayson, online at omniaaudio.com/9.
And now, our feature presentation.
TWiRT.
Let's get up to speed on audio coding, streaming, and processing. You need to know this stuff, and our own expert, Goran Tomas from Europe, joins us.
All right, calm down. He says that to everyone.
This calls for immediate discussion.
What's up, Doc?
All your days are belong to us.
From his palatial office of important business,
or in a choice hotel in a distant land.
This is Kirk Harnack.
Chris Tobin joins me to interrogate Goran Tomas from Zagreb, Croatia. Audio coding, tech, and processing for it are the hot topics.
You're dialed in to This Week in Radio Tech.
It's time for This Week in Radio Tech. Hey there, I'm Kirk Harnack. I'm so glad you've joined us. This is kind of a special edition of the show. We had to postpone our usual Thursday night soiree to do the show on Friday morning, and that opened up an opportunity. Normally on This Week in Radio Tech, we do the show in the evening in the U.S., and so it's really difficult to get a guest who is an engineer in Europe, because by this time, everybody in Europe is, nighty-night. They're all asleep. So because we're doing the show on a Friday morning, we're able to get a guest from Europe. And our guest today is a guy that I've wanted to have on for a long time. We'll introduce him in just a minute. First of all, let me bring in one of my usual co-hosts from New York City, the best-dressed engineer in radio. It's Chris Tobin. Hey, Chris. Good morning.
Hello, Kirk. How are you? I hear you're a little under the weather.
Yeah. Yeah, I am. Are you feeling good? Because you may have to host if I have to cough too much.
Yeah, no, I'm in. I can say I'm in good shape despite the oncoming bad weather we have coming, and getting ready for AES as well, just like you. So, you fortunately will be flying back into probably good weather. I fly back into a storm.
Oh, that's right. So when's this? This is Hurricane. Is it Sandy?
Hurricane Sandy and a weather front from the west are going to collide sometime around Monday evening. I arrive here in the New York metropolitan area around Monday evening, and it intensifies sometime between the overnight Monday into Tuesday.
This is the perfect storm. We had a perfect storm in '91, I believe.
That's correct.
And
yes,
so
they're predicting the barometric pressure to be somewhere in the vicinity of 950 millibars.
That's pretty low.
That's low, and they used the concentric ring map on the television this morning on the Weather Channel, and the tighter the rings got, the higher the winds. And guess where they get real tight?
Where? Right over LaGuardia?
Right over the New York metropolitan area.
Yeah. Those tight rings of I guess some people know, some people don't. I'm actually a qualified meteorologist, or I took all the schooling for it. And yeah, when you see those barometric pressure charts, the tighter those rings get, that means the pressure gradient over distance is very steep. And
yes,
a steep pressure gradient always means high winds. And the wind is typically going parallel with that pressure gradient, always heading slightly in toward the low pressure, but generally speaking, fairly parallel because of the what's the word I'm trying to think of? Not Coriolis effect. What's the word I'm trying to think of? That makes your bathroom drain spin the right way or the wrong way.
Oh, I had you talking about this.
Yeah, that effect. Anyway. If it weren't for that effect, the wind would go from high pressure to low pressure straight, and it would go across. It would go tangential to those pressure lines. But because of this effect, somebody in the chat room will correct me and tell me what it is. Because of this effect, we end up getting the wind going parallel almost to those lines. So anyway, if you see the lines, that's where the wind is. Oh, gosh. Well, listen, good luck getting back into New York on Monday. I'm coming to Nashville, so it should be just fine on Monday. Enough about that. Let's bring our guest in here on this edition of This Week in Radio Tech. It's our guest is from Zagreb, Croatia on Skype. It's Goran Tomas. Hi, Goran. Welcome in.
Hello, Kirk. Hello, Chris.
Hey, we're glad to have you in here, Goran. So, Goran, you've had a few interesting jobs in the last few years. It seems like for a while you were working in a university setting. Tell me about that.
Well, there's actually been a college radio station kind of attached to the university that I've been working on for like 10 12 years. Currently working at a Radio 101, which is basically was top-ranked radio station here in Zagreb. Also worked there for 12 years. Then went to UK and developed some audio processing. Came back to work for a system integrator here in Zagreb, which actually has offices in various countries. AVC, maybe people have heard of. Some of our colleagues have been on the show already. Yeah, and that's about it.
Cool. And I understand that in your work with the radio station, you had an opportunity. See, I ran across your name on a white paper. I call it a scholarly paper because I was just very impressed with what you had to say in this paper. Seems like I was at an AES convention in Europe. I think it was the one in Vienna a few years ago. And I saw this large display of this blown up huge, the poster size or bigger, this scholarly paper written by Goran Tomas, where you were doing some comparison of different audio codecs. Can you tell us about what that paper was about?
Yes, yeah, that paper was written while I was still in college, kind of as a part of my master thesis. Basically, it was about audio processing for digital radio and about audio coding for digital radio. So digital radio kind of in a more general sense, meaning DAB in Europe, HD radio in United States, and web streaming as a platform for all stations around the world.
Gotcha.
So the paper kind of was two-folded. One was describing the best practices for encoding the audio, which are the currently best codecs to use, which bit rates, which are typically used in DAB, which in HD radio, what to use for web streams. And then the other part was about audio processing and how it can help web streaming, and what are some of the caveats you have to be aware of when using audio processing and streaming in general, and digital radio. Basically, digital radio and web streaming are kind of very similar. It's just a different transmission medium. Otherwise, it's basically the same thing.
Sure. Hey, let's take the opportunity on this show, since we've got Chris Tobin here, and Chris now heads up a company that does both audio and video coding for streaming purposes and backhaul and such. And also we've got me. Of course, I work for the folks at Telos. Telos is in very tight with the folks at, say, Fraunhofer. We have a long relationship with them. Goran, I wonder if you might kind of take us through a little bit of an educational exercise about audio coding. Certainly we've talked about this before, but we've never really heard it from someone over there in Europe, and so much of this audio coding has been developed in Europe, whether it's perceptual audio coding, the folks at Fraunhofer, and then the folks at APT also have developed audio coding that's often used in professional applications. Talk to us a bit about your thoughts about perceptual audio coding and non-perceptual audio coding, just where you think we're headed with audio coding. Will we always have it? Is it really necessary? Are there good ways to use it really well to where it doesn't cause any problems? Kind of take us through a bit of your thoughts about audio coding. And Chris, let me invite you to jump in any time with any questions.
Certainly.
Well, I would hope that we would not have to use it in the future. Audio coding is a great way to get good quality audio over bit-reduced networks and pipelines, but it's a kind of a necessary evil. So in future, with internet connections, the bandwidth being ever expanding, we will not have to use audio coding at all. All we will use something that's lossless for audio coding, which I'd like to touch up maybe later in the show. about the lossless coding, because I think that's kind of the next step going further. So far, we've used mostly lossy coding, perceptually coded audio, which has kind of evolved from something back in the late 90s, 2000s with real audio and the Windows Media at the beginning, and it sounded quite squishy and swashy and underwater, or whatever words people use to describe the artifacts. And then came MP3, which was perhaps I mean, at that point we probably already had the higher bitrate, so MP3 could be used as a typical format.
Well, and we had MPEG Layer 2, which was compared to today's codecs, was not very sophisticated. Of course, we still use MPEG Layer 2. It's designed for higher bit rates, preferably like 256 kilobits or thereabouts. But was MPEG 2 the first real or the first popular perceptual audio codec where we took modeling of what the human ear pays attention to and what it ignores, and we're not going to code what the ear ignores. We're just going to code what the ear perceives in typical modeling. And that let us reduce the bit rate a pretty fair amount by using that model, right?
Yeah. MPEG Layer 2 was the first codec to be used, and it basically, like most codecs, it relies on psychoacoustic effect of masking. So basically, if there is a strong tonal component at one frequency, our human hearing kind of has a mask around this tone, and every frequencies below the mask we will not actually hear because it's being masked by this stronger tonal component. So that's used to then kind of just disregard or throw away frequencies that the perceptual coder anticipates we won't hear.
I want to mention something that if you're an engineer out there and you want to try this for yourself and you have the equipment to do this, it doesn't take much. If you have two tone generators and some way to look at the mix of, if you mix those together, and then some way to listen to that, and some way to look at that on a spectral analysis, and there's plenty of computer programs that are free or close to free that you can use to real time look at a frequency domain, spectrum analyzer analysis of those tones. What you can do is, bring up one tone, let's say a kilohertz, and then bring up another tone, not as loud, but somewhere under that, at let's say 1100 hertz or 1050 hertz, somewhere near a kilohertz, but not a kilohertz. And you listen to this and you hear the kilohertz tone, and you bring up you can look at the spectral analysis at the same time. You bring up the other tone that's close by, as long as it's below in level the kilohertz tone, you don't hear it. Your ear just does not hear it. And the first time I saw this, I was just amazed at, wait a minute, I see two tones on there. Yeah, one's louder than the other, but I see two tones, and yet I don't perceive two tones. I only perceive one tone. Now, if you move that lower volume tone farther away in frequency from the kilohertz tone, so you move it down to, let's say, 800 hertz or up to 1500 hertz, then there's a point where you do hear both tones. And so spectral masking uses this effect of the human ear to say, you know what, you can't hear that tone that's nearby and lower in level. You can't hear that part of the audio, so we're not going to code it. And one of the differences in MPEG Layer 2, MPEG Layer 3, and the newer AAC algorithm family is the number of spectral bands that it divides the audio up into. And if I recall correctly, it seems like MPEG 2 is 32 bands, MP3 is 512 bands, and I want to say that AAC it might be like 2048, some very large number of spectral bands that it divides it up into and works on each band separately. So I'm sorry, Goran, I didn't mean to interrupt you, but I wanted to inject that thing about the spectral masking and just how amazing this effect actually is. And by discovering this spectral masking, this is what allowed the engineers at Fraunhofer and other companies who worked with them to seriously reduce the bit rate without affecting the audio quality very much. Other coding schemes had depended upon, like ADPCM, had depended upon just some curve fitting or describing the delta between one sample and another sample and reducing that. So you weren't actually transmitting the value of each sample, but you transmit an initial value, and then you just transmit smaller numbers indicating up or down, up 3, down 2, up 5, down 100, for the next, for subsequent samples. And you could reduce the bit rate that way, but it was the spectral masking that really allowed a big reduction in bit rate with subjective to a lot of conditions without a huge drop in audio quality. Go ahead, Goran. I'm sorry. Go ahead.
Yeah, that's exactly right. That's what happens. Basically, there's on this kind of a tone that you have, there's kind of a blanket over it. So everything under the blanket, all the spectral components, you don't actually hear. And that's frequency masking, and that's the key that made perceptual coding possible. But then there's also a temporal masking. So in time domain, when you have a strong transient, the ear doesn't hear anything before the transient's about 10-20 milliseconds, and then after the transient either. So you can remove audio before and a bit after the transient, and you won't even notice this.
I've seen this effect described, Goran, and I can understand this effect. If you look at, there's a paper written by Steve Church, the late Steve Church, the founder of Telos. There's a paper on the Telos website, telos-systems.com. If you go into the white paper section, there's a paper about AAC audio coding. The title is something like AAC. He's comparing it with drinking a beer or something. But in there is a diagram that shows how temporal masking works or what its effect is. And you're right. You can, let's say that you have let's just say this 1 kilohertz tone you're listening to, and you have this masking effect in the frequency domain. But if you then quickly remove the 1 kilohertz tone, there is a short period of time where the masking effect still takes place, and then it ramps down to where it doesn't take place. So the ear has this, or the ear-brain combination has this effect where it won't hear, those nearby tones unless they poke up above this psychoacoustic mask. Now, what I kind of get that at the end of the tone, that your ear and brain may not be sensitive for a short time to things, so it takes a moment for the mask to drop off. But what I don't get is this temporal mask that occurs before the tone. I don't get that. That's like, how is your ear not so sensitive before the tone starts? But apparently that is a small part of the masking effect in the temporal domain.
Yeah, I'm afraid I don't have an explanation for you there, why this happens. Why do we hear this way? But it does. I mean, if something is going to, I don't know, explode near you, you would not hear anything before that. It would just be masked by this loud tone. And it's kind of a compression in the hearing itself. That's part of this. But the good thing is that this effect can be used, for example, in look-ahead limiting. Because in a look-ahead limiter, the limiter will kind of look ahead audio and then start decreasing before the transient comes, which needs to be controlled. And because of this temporal masking effect, we don't hear this attenuation before
Well,
the.
and I'll just mention one more time before we move on that the whole this temporal masking is key, because if you consider this imaginary mask over the tones that are of interest, both in the frequency and the time domain, what psychoacoustic masking tells us is that we don't have to encode any energy that falls below this mask. So if you've got a really loud piano playing some notes, and you've got a violin in the background playing nearby tones at a reduced level, I don't know if it's typically 10 or 15 or 20 or 30 dB lower, but some degree lower. Again, those frequencies must be close. If it's a far away, if you're playing a piano and the violin is playing a much higher notes, then you need to record both of those, because the violin doesn't fall under the spectral mask of the piano tones. It falls above the mask, so you have to encode it. But if you're playing violin notes lower in volume but still near in frequency to the piano ones, you don't have to encode the violin. You can't hear it. Fortunately, most instruments, are of quite different timbre and spectral range, so we end up encoding, all of it. But you can hear this effect if you listen to especially a lower bit rate psychoacoustically encoded piece of music. You can hear this effect take place, and it's not pleasant at lower bit rates, and you realize something's missing. At higher bit rates, it's not a problem, or it's barely a problem, and you don't notice it, and you can even do several passes of this psychoacoustic encoding, and it doesn't hurt you until you get to a whole bunch of passes. Anyway, I'm sorry, Goran, please carry on with your explanation.
No, yeah. I mean, basically, those are two perceptual effects that we use in coding, and then there are some mathematical ways to reduce the number of bits, such as representing the most frequently occurring values with a smaller number of bits, and then those that occur rarely, we use more bits. So that's one way. That's more of lossless type of encoding, but one more way to reduce the data rate required to send the audio.
I want to bring Chris Tobin into the discussion here. I got started back in this business of reduced bitrate recording back when I worked at Scott Studios in the mid '90s. And we were, Scott Studio Systems at that time, were exclusively using aptX or aptX brand audio encoding. Now, back then, hard drives, big hard drives, were not available. The biggest hard drives we could conveniently get were 9 gigabytes. And this was too small to fit an entire radio station music library on in the uncompressed format, like a WAV file. So we had to do reduction, and we happened to use aptX encoding. And Chris, with automation systems that you dealt with, I'm sure you've experienced the same thing, where we in the 90s and early 2000s, the cost of bitrate reducing was less than the cost of hard drive space. And so we bitrate reduced songs and commercials and such onto our automation systems. But at least in terms of hard drive space, that's not true anymore. Now the situation has changed, and hard drive space is cheap. So, Chris, what's the best practice for a broadcaster or a podcaster, anybody who's storing audio?
Well, I would agree with you that, yes, back in 95, 96, we were doing automation, and aptX and MPEG-2 are the popular methods of encoding. And we made it work, but MPEG-2, you can get away with 256 kilobits and have a reasonable sound both in music and voice, which worked out well. And drive storage space, you can make the price point work. Years later, we moved to a WAV format, uncompressed, because the cost was much easier to manage as far as hard drives. But moving forward, I mean, if you're, I am a fan of uncompressed audio storage. A friend of mine is an archivist, and we've worked together on a couple of projects. And at the end of the day, if you can preserve the quality of the audio source, whether it be spoken word or music or anything of that sort, uncompressed is the way to go. And cost now with hard drives and the technology is available to back up and protect those hard drives. So that would be my suggestion. Go uncompressed. Now, if you're a podcaster or somebody who's doing work where your budgets may be more limited, if you're going to go with a bit reduced algorithm, I would choose something along the lines of AAC or a lossless type method, and then use the highest bit rate you can afford on the hard drive space. But take advantage of hard drive technologies that you can back up. Try not to get too crazy. We did discover, I will say this, we discovered that the higher density hard drives, like the terabytes and stuff, or approaching terabyte size, because the sector spaces had to be made smaller and everything else about the surface is much smaller, we found that failure rates or corruption was higher when it came to the storage of music and all this stuff because of the constant accessing back and forth. So if you're in a mission-critical broadcast environment, you may want to consider a smaller drive, not maybe not a terabyte, but just below that. Or if you're going to go with terabyte drives, try and increase the sector size so that the audio doesn't get fragmented as much, and that reduces the read-write cycles and access times. I know it's subtle stuff, but believe it or not, we discovered a few things that made the difference at the music stations I worked at, as well as the all news stations, and we had a lot of stuff going on, networked drives like crazy, and it was interesting. But I guess rule of thumb, if you can afford it, which nowadays you pretty much can, I'd go uncompressed. If you are tight on the budget, look for a lossless type approach. AAC has been really successful on a couple of projects I've been on, or APTX, I believe, also still offers a very nice alternative. And just look at things from that perspective. Also, try the highest bit rate you can afford, because I agree with both of you that the higher the bit rate, the better chance you have of preserving the original sound in a bit reduced environment.
Couple notes there I want to hit on, and actually this is the first time we've mentioned this on this show. Something that Chris Tobin just brought up, and that is that these high density hard drives. Hey, I was listening to a podcast earlier this week where I confirmed what I suspected, which is that the densities on hard drives nowadays are so high that there's no longer necessarily a perfect relationship between the data that you put on and what is actually stored on the hard drive. They have to manipulate the data for writing and reading on the hard drive such that they use algorithms to predict, okay, here's the data I've got to store, but if I store it exactly as is, I won't be able to read it because the pits are too small. The areas of magnetism one way or another are too small. I'm going to have to encode this data in a different way such that I can actually get it back off the hard drive. So that they're now actually doing I'm not going to call it bit rate reduction, but bit manipulation onto the writing and reading of the actual hard drive. This is done in the hard drive electronics, not in the operating system, such that the ones and zeros that you give the hard drive are not necessarily what goes on the hard drive, but it is what you get back, or it's what you're supposed to get back, because the densities are so high that the difference between a 1 and a 0 is so small and so not necessarily 100% predictably readable that you have error correction just out the wazoo now on modern hard drives. So it'd be interesting to find out what size of hard drive you buy where they haven't gone and used the same error correction techniques, but you actually get a much more firmer, you get a better write and a better read because you've got more space to do it. It'd be interesting to see from the manufacturers what hard drives, and maybe these are hard drives that are meant for media storage, because they have in the past, I imagine they still do, have hard drives that are intended for reliable media storage. So a consumer 1 terabyte, 2 terabyte, 3 terabyte hard drive, not necessarily the best choice to use for storing media that you've got to have access to reliably over and over and over and over again. I say that one thing.
Archivists that you have to be careful if you go that high.
Yeah. So the other, but I'm not eschewing linear storage. I think we ought to store audio linearly because it is so cheap to do it. The other thing that I want to point out is, though, and it's been mentioned in the chat room that, hey, linear is the way of the future. Compression's going away. Well, I would remind us that there's always going to be the desire to listen to audio and watch video in a mobile environment, and that implies RF. And RF implies a limited amount of bandwidth for all the users to use. And sure, coding technologies improve over the air. We get more bits per hertz all the time. We also have, hopefully, more spectrum available, as in the U.S., for example, the FCC pushes more TV stations out of their traditional channels, gets them into a smaller number of channels. More bandwidth opens up for the mobile carriers to use to distribute internet mobile connectivity. But it's still going to be a finite resource as far as we know. I mean, you can buy all the hard drives you want and load them up, in a big warehouse. It's nearly infinite. But RF bandwidth is going to be a finite resource. So I think that coding for that last mile, especially over RF, is going to be with us. Now, here's a thought.
Yeah.
Here's a thought. What if someday we live in a world where all audio and most video distribution on the internet turns out to be linear, but when it hits the carrier, the mobile carrier, they do the bitrate reduction for that last mile to the user? I mean, what if the carriers got in the business of bitrate reduction for their subscribers? That might be an interesting world to live in.
Yeah, I mean, definitely. When I mentioned the lossless coding, I was aiming at web streaming, because this is a medium that grows in speed and bandwidth, unlike the RF channels that we have, that are limited in bandwidth and probably will always be limited. To emphasize what both Chris and Kirk you said about using linear audio for your music storage and for all audio playing on a radio station, I would definitely support that. And the other crucial thing is when encoding, use the highest bitrate that you can get away with. And sometimes people forget that because perhaps some of the marketing materials from product that use encoding, or even the people that invented codecs, lead you to believe that you can get away with low bit rates and still have great or CD audio quality. But that's not necessarily always the case. So it's always best to use the highest bitrate that you can afford and that you can get away with. So if you're doing HD radio, web streaming, or something like that, there's probably a couple of stages of encoding that your audio will go through. If you're a reporter on the field, records something, something for a news bite on a portable recorder, probably that's already being encoded to a format. And if you're going to edit it, hopefully it will end up as linear in your playout system, but maybe not. And definitely for web streaming and for digital radio, you will have the encoding for the transmission medium. So that's one more reason to avoid coding everywhere you can. If you can't, then use the highest bitrate.
Sure. Hey, for those of you tuning in, you're watching a special edition of This Week in Radio Tech. Normally, we're on at 8 p.m. Eastern Time on Thursdays here on the GFQ network. Today, we had an event on Thursday evening to go to. It was the Microsoft event. So we're doing the show on Friday morning in the U.S. on the East Coast. This week in Radio Tech, our guest is Goran Tomas from Europe, and he's an expert in audio coding and also audio processing. We're going to get to the audio processing in just a moment. Also with me is one of our usual co-hosts, and that is Chris Tobin from New York City. So glad that you're with us on this episode 142 of This Week in Radio Tech. By the way, as we were talking, we have this desire to do linear audio everywhere, right? And yet we have breakup on a Skype call. Some of Goran's words were broken up on his call with us, and that shows packet loss, and that kind of emphasizes the need to use less bandwidth when you can, when it's appropriate. I was noticing, though, that typically when we do this show on a Thursday evening, I get a certain amount of packet loss between my office and the GFQ network. Typically it's under 1%, but there's some packet loss, and sometimes it jumps up a little bit. I'm noticing that on this call, I don't know what you're seeing from me, but my technical window here is showing zippity-doo-dah for packet loss. I've lost a grand total of 66 packets, in the last 45 minutes. That's pretty amazing. Why is that? Nobody's watching Netflix right now. Maybe that's it. The internet
probably.
usage here in Nashville is way down right now, at least in my neighborhood, compared to what it normally would be.
Is at work, so
Yeah, everybody's at work. They're using the bandwidth downtown. They're not out here in the burbs watching Netflix. Hey, we need to take a quick break and hear from our sponsor this week. Our sponsor is Omnia Audio, and I want to talk about the Omnia 9 audio processor for just a moment. Now, rather than me tell you about it, I want to bring in Goran, our guest, because Goran has just spent several days, maybe a couple weeks, with Leif Clayson. Leif is the inventor of the Omnia 9 audio processor and a whole bunch of audio algorithms and improvements in the way we can deal with audio to have it sound consistent and good and yet loud. If you want it loud, and bring out the prettiness of it, fix problems with it. I shut up. Goran, tell me what you and Leif learned together as you're going around and what kind of reaction that you got from broadcasters as they were installing Omnia 9s.
Well, we did a couple of weeks as a European tour for the Omnia 9, and basically, Kirk, I can tell you, every station that we visited, at first, they're a bit skeptical about the new product and about the Omnia 9 because it's so different to all the other processors. But once people hear it, they are typically by the possibilities, the features, as well as the sound. I mean, it's probably the only processor on the market that kind of tries to first restore the dynamics of the audio to something that would happen if the mastering engineers would not squash and clip CDs as do that. So it has this undo technology that consists of a declipper and then the program-dependent expander. And then there's the dynamics processing, as typical with any processor, but here, it's very flexible and selectable between 3 and 7 bands, and the various options that you have for tailoring the sound, parametric EQs and side chains, and finally, one of the other key features, at least for me, is the psychoacoustically distortion canceling clipper, and you basically have to demo the unit, see this for yourself, because it's so radically different, and I mean, it sounds very different to any other processor on the market.
One of the things that to me is kind of amazing about Leif's technology in the Omnia 9 is instead of what Leif calls a stereo generator, what Leif has is what he calls a stereo embedder. And it uses an interesting trick that, well, we've known about this trick for years, but Leif's actually been able to make it work well. He is able to adjust the position of the stereo pilot. That's that 19 kilohertz tone that tells home radios, hey, turn into stereo now, and also provides a reference for the 38 kilohertz left minus right subcarrier. But the stereo embedder is able to give you an interesting effect. I've always hoped that this was possible. In fact, I talked about this with Frank and some other engineers years ago, and that is you do 100% modulation on your mod monitor, okay, 100% total modulation, but your left and your right channels, when they're decoded, they are going well over 100%, giving, indicating that there's more loudness there in the left channel and more loudness in the right channel than you ever saw before. Traditionally, you get 100% total, you get 100% left and 100% right as the meters are moving around on your mod monitor. But with Leif Stereo Embedder, you actually get readings upwards of 110, 120, 130% left, and the same on the right channel decoded. So you get some loudness there you didn't have before because of this stereo embedder. If you want to check it out, go to the Omnia Audio website. It's on the web at omniaaudio.com. Check out the Omnia 9 audio processor. It's gorgeous. Leif Clayson invented it, and in collaboration with Omnia, it is a real product. It's been out for almost a couple of years now, and it's on the air at a whole lot of radio stations. So, hey, Goran, thanks for sharing your experiences with Leif Clayson with us and what he's doing there. I want to move on. Again, this is This Week in Radio Tech, number 142. With us is Chris Tobin in New York and Goran Tomas from Zagreb, Croatia. We're going to move into the section of audio processing talk here in just a minute, but there's one more thing I want to hit on. I want to bring Chris Tobin back in the conversation. Chris, your company that you work with, Musicam, excuse me, got this cough going on. You guys make audio codecs. And tell me what you guys see in the future for audio coding. We've been talking about, hey, yeah, let's go to linear. Let's all do linear. The internet's getting better. But there's still, I mean, in real life, we still need to code audio. What are you guys doing to help broadcasters?
Well, at Musicam, we've got the audio codecs that actually a lot of our customers now are moving to PCM on their IP side, believe it or not, where they have the bandwidth. They're actually, we've got, we've got two different types of customers that we're seeing. And the future, I believe, holds probably lossless encoding where possible, where feasible, both bitrate and because the end user just needs to do it that way. And then PCM or uncompressed in the backbone. So I've got a couple of customers now looking at PCM-based stuff, basically back and forth internally, and then doing sort of like, I guess, AAC at the highest bitrate they can afford to go with, and that's what they're using for downstream. So we've also got a couple of customers now doing HD radio, and they're worried about the cascading of algorithms, and we're starting to hear from folks about that. So what we've been doing is our codecs, basically we're doing all the algorithms possible, offer as many bitrate selections as possible, and then let the customer just choose. But in the future, what we see as a company, I agree with Goran, we still will need some type of bit-reduced algorithm or bit-reduced encoding, because that's just the way it's going to be, whether it be mobile environments, whether it be rural environments where maybe bandwidth is still at a premium. In urban areas where it may become no longer a premium, it won't matter. So I'm thinking the scale is going to be both those who can do it uncompressed and those who know how to manage it will go with the bit reduced, but at the highest bit rate possible. And that's what we're getting a lot of calls for. I think personally, what we should be focusing on as an industry is getting after the carriers and the infrastructure folks, the backbone folks that provide the pipes, we'll call them that, the data connectivity, and get them to be more diligent about proper management. Just as you pointed out, Kirk, today at this time of day in your place, bandwidth must be good, or shared bandwidth must be good, because you only had 66 packets lost in 45 minutes, whereas tonight at 8 o'clock, if we were to do the show with the same setup, you'll find that it's almost impossible or difficult. Why is that? Because nobody is reining in the carriers. No one's talking to them and say, hey, guys, it's a known entity. We can manage this stuff. So the future holds, I would say, bit reduced, but very cleverly done, uncompressed, and then we need to get the in-between better managed. Otherwise, we're just going to continue this vicious circle or cycle of, let's do good quality. I can't do good quality now. I'll just have to give it up. And eventually the consumer doesn't know better. They're just going to go with whatever is easiest. It's going to wind up being 128K for everything, which we're discovering on many other music platforms.
All right.
Kirk, before we go any further, I'd like just to clarify the differences between some of the AAC codecs, because I see there a lot of confusion there.
Sure. There's a huge family of these things, these AAC.
Exactly,
codecs.
yes. And people, when you ask people what they use, I use AAC. Which one? Because they're quite different. So let me just go over, basically after MP3, the Fraunhofer people developed AAC. And that's the successor of the MP3, and it's about 30% more efficient, has, like you mentioned, more resolution of filter banks and other stuff. And it's a very, very good codec, and it can be used for a lot of things in radio transmission, storage if you have to. But for didn't have this bandwidth on the ADSL and cable lines, and we still don't in many countries and states. The AAC, the high efficiency AAC was developed, which essentially uses AAC to code the low band, and then uses something called spectral band replication to encode the high band. And the spectral band replication is a technology that describes the high frequency content with just small data. So thus reducing the requirements for the bitrate.
Yeah, it's kind of like a shorthand. When you see a codec that has the letters HE for high efficiency, or maybe a plus sign, for AAC plus, that was used for a bit. Then you have this technology, spectral band replication, where, as you said, the bottom half of the audio, let's say a 15 kilohertz audio or 20 kilohertz, the bottom half is really coded, but that's easier to do. It's easier to code lower frequencies, takes fewer bits to do it. But then the upper frequencies are described either as harmonics from the lower frequencies or perhaps as their own standalone frequencies. But you're right, it's a shorthand that describes it. And so it isn't perfect, but in practice, I think it's gotten pretty good. There are some bad implementations of players, and Greg Oganowski has pointed that out, that some AAC plus or HEAAC players don't do a very good job at all. But if you listen on a player that really works well, I'm not saying it's perfect, but I'd listen to it all day long and be happy if I know that, hey, it's for entertainment purposes, not for critical listening purposes. Go ahead.
Yeah, but I just want to point out that the AGAC, there's also version 2, which uses parametric stereo and can go a bit lower in the bitrate. But AGAC was designed for very low bit rates. And when I say very low bitrates, I mean 64 and below. So if you are going to use 96 kilobits or 128 or higher than that, then you really want to use AAC, standard AAC or AAC low complexity, because that would sound much better. Actually, 128, it's nearly indistinguishable from the original. And I see a lot of people kind of using 96 kilobits, but they use AGAC, which is not designed for that and will not sound as good as AAC alone.
Yeah.
So just that's one thing that I wanted to point out, that there's different AAC codecs and they are designed for different bit rates, and you to achieve the best results, you have to choose that you want.
There's a new codec that some folks have been talking about, saying, hey, this is new open source codec called Opus. Do you know much about Opus at this point, Goran?
No, I don't. I actually just heard about it with this European tour and didn't have the opportunity to check it out. I did hear about HD AAC, sort of high definition AAC, which is actually a codec that allows lossless encoding, so fully transparent audio. If you have enough bit rate, then that would be around 760 kilobits, 800 kilobits. But also has an AAC core codec. So if the bandwidth that you have is lower than that, it will actually do a smooth crossover from fully lossless to something lossy, all the way down to the core codec itself, which can run, for example, at 128 kilobits. And if you have only 128 kilobits, you would only listen to AAC encoding. If you have a 500 kilobits, you would hear something between fully lossless and this AAC. And if you have 800 kilobits, you hear lossless audio. And we talked about future. I think that's the future for I hope that will be the future for web streaming, at least.
That's a very cool idea, and especially good for let's say private backhaul. If you're using like a broadcasting company has a private WAN, and you might normally have 800 kilobits available for a stream, but you might get pinched sometimes and have less. Well, then that codec could automatically degrade to something less. One thing I want to point out, there has been some buzz about this Opus codec, and folks say, hey, it's open source, so you can use it. It's great. And we've done some looking into Opus at Telos, and we're excited about it. There is a problem, though, with using open source codecs, and that is that not everything in them is unencumbered from patents. And so if a company wants to incorporate Opus and it's free, then may not be a problem. But a lot of and I'm not rendering an opinion on Opus in particular, but I will tell you that the licensing agreement for Opus it includes verbiage that basically says, by the way, if something is found in here that somebody really does have some intellectual property claim to, then we're not responsible. That's on you. And so unfortunately that's a kind of a tip off right there for corporate attorneys to say, ooh, well, that may be tough for us to incorporate because we could get sued later on, because they're basically saying that there might be some stuff in here that belongs to other people, and so it's a little bit of a sticky wicket. We at Telos are looking into it. We'd love to offer it, but not sure just how we'd be able to offer it. Then there's the question of, does it really offer advantages? I mean, on the one hand, some people like open source just because it's open source, but that doesn't necessarily mean that it has real advantages over something that you might have to pay a little bit for. So anyway, that's just my thoughts, and more thoughts to come on that as we find out more. I wish our engineers could just plop it right into some of our codecs and use it, but ain't necessarily all that easy when you're charging dollars for the rest of the product. Boy, we're going to run out of time here to talk about audio processing. And that was Goran said, hey, Kirk, I'm really good at processing. Let's talk about that. So let's switch gears real quick and hit on a few high points of audio processing. Goran, this is always a very subjective conversation. Everybody has their favorites, like, hey, I like a Ferrari, or I like a Chevy, or I like a Camaro, or whatever, a Ford, or whatever it may be. And so I know you've got a few thoughts to share about audio processing nowadays. And maybe we should limit our discussion of that for the next 5 minutes, is about all we've got, to audio processing for encoded audio, since that's the way the world is headed and already there. So whether it's HD radio, DAB, DRM, internet streaming, audio for video that's being streamed, let's hear some of your thoughts about the right way to be processing audio for an encoded audio path.
Yes, so basically if you're going to use web streaming, HD radio, digital radio, you want to use a processor that's designed specifically for that. You don't use FM processor because that will employ clipping, and clipping will cause additional spectrum to be added to the audio, which then the transmission codec will waste bits encoding. And it would you would get more artifacts, more distortion than needed. You would also have a 15 or 16K low pass filter on the audio, and the FM processor would be designed for pre-emphasized audio, and to handle that, and you would increase kind of the high-end density, which again is where most codecs have most problems with, and most artifacts. If you listen to encoded audio, most artifacts are in the high end, they're not in the low end. So definitely don't use FM processing. Use a processor specifically designed for digital radio or web streaming, and that one will use a look-ahead limiting, which is a very clean way of limiting peaks to a tightly peak control level without adding additional harmonics. It will also have a full 20 kilohertz bandwidth, which hopefully the transmission codec will pass. It has enough bit rate. if it's AAC at 192 or 256 or something like that. You also want to be aware of the codec overshots, because when codecs are fed with tightly peak-controlled audio, they sometimes overshot. As some codecs are more notorious for that, like the high efficiency AAC, it will definitely overshot in the high end. AAC not so much. Some others, depending on which bit rate you use. So you want to leave some headroom. You don't want to feed your codec at a 0 dB full scale, because then any overshots generated in the codec will get clipped and will not sound good. Perhaps one more thing to take care of is the stereo width. You don't want to excessively increase the stereo width, because a lot of processors today have stereo enhancers that can do that. Because most of the perceptual codecs use some kind of intensity or phase encoding to reduce number of bits they use for stereo encoding. So they will use joint stereo or some other techniques. And if you have a too wide stereo image, then this will increase artifacts. Some processors will even allow you to reduce the stereo image, and that is very useful in this scenario. So just very quickly, some of the points when processing for digital radio and web streaming. If you use a very low bit rate for your streaming, and for example you use HEAC, you might want to employ some high frequency filtering intentionally. So you might want to reduce the bandwidth that the codec is fed with, and this will actually reduce the artifacts and not affect the frequency response so much. So I think that's essentially the key points. Hello.
Okay. Well, I would agree with that. I know I've done audio processing for streams, web streams over the years, and I've always gone with the rule of thumb. Keep the audio within the spec, no overshoots where possible, and do not feed the encoders with complex compressed audio, I'll call it. And I've also done some little funky time delay stuff, but that works the best. You're absolutely right. And that's even with the earlier codecs that I was dealing with, but most recently I've helped with some folks set up their web systems, and they all had everything cranked. And a couple of places had processors, some defunct FM processors that they just bypassed the stereo generator and used everything else, and couldn't understand why certain things sounded good and other things just did not. To your point, processing with something that's designed for bit reduced audio streams makes sense.
And that's a very good point, Chris, and thank you for reminding me that you don't want to process audio too much. You don't want to be aggressive with the processing for digital radio or for web streaming. And we've actually done a blind listening test with students at the university with increasingly aggressive processing that's then been encoded AAC at 48 kilobits. And people noticed the difference when we used aggressive processing versus more relaxed processing. So the audio does get worse with aggressive processing after encoding, as well as there's some other effects like fatigue and stuff like that when you use too much processing and you reduce the dynamics too much.
Oh, absolutely. Absolutely. I would agree. And I know I've done tests both over the air with HD radio, which again, basically put it in simplest terms is a stream, is an MP3 type stream or an AAC type stream that's put on an RF carrier and brought out to a radio. So that's basically what you're dealing with. So to your point earlier, HD radio or web, those do need to be treated as digital streams and not just traditional audio paths. And when I did some tests with spoken word on one of the stations I worked at, and we found that, as you pointed out, the more compressed, I'll call it, the more processed the audio coming out of the studio going into the encoders, it was fatiguing. We did actually get audience response on several levels. So we went the other direction, which is something I've always been a proponent of, even in the analog days. And there's ways to make things work. But you're absolutely right. With today's digital, 0 dB full scale is very dangerous if you're not careful. And also, I've discovered that most codecs do not like to see anything above, the -20 reference on some, depending where you are, -20, -15, depending on who you use. And it seems to be they fall apart real quick when you approach that 0 dB full scale line. Maybe it's intentional. Maybe you have no choice because it's just the way the digital systems have to function with filtering and whatnot.
Yeah.
Guys, we have come to the end of our hour, and unfortunately, the airplane that I have to catch will not wait. So we're going to... I was told that Andrew Zarian has lots of hard drive space, and we could go on as long as we want to, but sadly, I can't. So I got to go. Hey, Goran, it has been a pleasure to have you on the show. I'm glad we were able to do a show at a time that you're not sleeping. So good to have you here from Zagreb, Croatia.
Yeah, it was great to be on the show, and thank you for inviting me.
Also, your friend Charlie N4FA says hello.
Okay. Hi to Charlie.
All right, Goran, we'll have you back on another show, and I appreciate very much you being here. I know you've done a lot of hands-on work in this area, both coding and audio processing. So I wish we had a lot more than an hour. Thanks for being with us. Appreciate it.
Thank you, Kirk and Chris.
And also Chris Tobin
thank you,
from New York City. Chris, thank you for being with us as well. I appreciate you setting aside time this time of day to do it. Are you headed for AES, Chris?
Yes, I'll be heading out actually tomorrow morning. I have a family matter to take care of tonight, and then after that, I'm flying out. So I'll be in San Francisco late afternoon. Hopefully
Good deal.
I'll be bright-eyed and bushy-tailed.
Good deal. And for those of you, a quick industry announcement. We're going to announce something kind of interesting. For years and years, the folks at Telos have been very tied in with the folks at Fraunhofer, and that's still good. No problem there. But we've had a number of requests for Telos products to include the aptX codec. Well, you're going to see that happen. There's going to be an announcement made at AES, and I'll be there signing a contract with Johnny McClintock of CSR, who holds the intellectual property for the aptX codec. And so that'll be a small event on Saturday night. So if you can be there and shake Johnny's hand, I'm just delighted that we're going to be having another codec option in some Telos products. So little industry note there. Hey, a lot of the other codec manufacturers already have it, and so now Telos will too, finally. All right, thanks for watching This Week in Radio Tech. This has been episode 142, brought to you by the Omnia 9 audio processor on the web at omniaaudio.com. We're going to see you next week on This Week in Radio Tech. By the way, a special time next week, too. It's going to be, I believe, on a Wednesday evening instead of a Thursday evening due to some other social engagements. So we'll see you probably next week. Hey, be sure you check our Twitter feed at TWiRT Show, just at TWiRT Show. That's our Twitter handle. And also you can find us on Facebook. If you look for us there, you can follow This Week in Radio Tech on Facebook. See you next time on This Week in Radio Tech. Bye-bye, everybody.
That's all the bandwidth we can pilfer this week. Another TWiRT has propagated, and all the transmitters and audio equipment live happily ever after, thanks to the handsome engineer and his kind, benevolent care. We'll be back next week.
Lord willing and the creek don't rise.
This Week in Radio Tech. Subscribe to iTunes and you'll never miss a show. Search for This Week in Radio Tech in the iTunes Store. Soliciting is strictly encouraged. If you liked today's show, tell a friend. If you didn't like it, we were never here. Kirk Harnack's wardrobe provided by the Salvation Army and the Red Cross Disaster Relief Services. Hair and makeup provided by Penelope Garcia Hernandez Weinberg.
He's unique, wouldn't you say?
I just want to get it over with.
This ends this transmission. Tango, Whiskey, India, Romeo, Tango. Signing off. Okay.